Good afternoon, everybody. Hope you guys remember me. In this new academic year, I'll be teaching functional analysis. So the subject name sounds a bit difficult, but it is basically the things that you have done or learned in the previous semesters. We are just extending it into a different level or viewing it in a different way. So in the beginning it may be difficult for all of you guys, but with the classes that you are attending, it will be pretty much easier for you to learn the subject. So despite all the difficulties that we are going through, it's with great pleasure that I'm sitting in front of you, and it is very interesting for me to use new platforms to reach out to you guys, and I hope it is interesting for you guys also. So let us begin our session. In this functional analysis, we have 3 modules. The detailed syllabus is given in your classroom, Google Classroom. You can refer to it. So let us begin with Module 1, Chapter 1, Section 1.1. In the beginning of this session, we are going to recall few terminologies which you have already learned in linear algebra, like linear spaces, independence, dependence, kernel, and so on. So let us begin. First of all, we are going to denote any linear space in this session using the capital letter E, and we are considering all the linear spaces over the field of real numbers or complex numbers. And functional analysis, in some cases we have to deal with both these fields together. So we mention the linear space E over the field capital F. So whenever we mention E over F, we have to keep in mind that it is basically the field of real numbers and complex numbers. Now some examples of linear spaces that are finite dimensional. Is R raised to n, C raised to n, and space of all polynomials whose degree is less than n. These are all examples of finite dimensional linear spaces. And if we consider the space of continuous functions defined over an interval closed interval AB, which is denoted by C of AB, we will get a infinite dimensional linear space. So C of AB is an example of infinite dimensional linear space. Next, what is meant by a linear map? A mapping A from E1 to E2, where E1 and E2 are subspaces, spaces, is said to be linear if and only if for every x and y belongs to E1, we can find scalars A, B such that capital A of AX plus BY is equal to A into capital A of X plus B into A of Y. Now, many examples of linear spaces are given in the textbook, page number 4. So you can go through these examples. Also verify whether these are actually linear spaces or not. We will come to the two terminologies which are associated with the linear map. The first one is the kernel of a linear map A is denoted by KERA, which is the set of all x belongs to E1 such that AX equal to 0. And the image of a linear map, it is denoted by IMA, which is equal to the set of all AX such that x belongs to E1. Next, we can show that kernel and image are both linear spaces. Also, we can easily prove that the kernel of A is 0. If the kernel of A is 0, then the linear mapping will definitely be 1, 1. So first, let us try to prove that the kernel of the linear map is a kernel of the linear map is also linear. So to show that the kernel is linear, we are going to take two elements, say x1 and x2 belongs to kernel of A. We must prove that it is the kernel of A is linear, and for that we have to show that x1 plus x2 is also an element of kernel of A. This is what we must prove. Now, if x1 and x2 are elements of kernel of A, we have ax1 plus ax2, sorry, ax1 and ax2 are both equal to 0. Now, what is a of x1 plus x2? This is equal to a x1 plus ax2. Why? Because a is a linear map. Now what is ax1? ax1 is 0 and ax2 is again 0. So we get a of x1 plus x2 is 0. So since a of x1 plus x2 is 0, we can say that x1 plus x2 is an element of the kernel of A. So we have shown that if x1 and x2 are elements of kernel of A, then x1 plus x2 is also an element of the kernel of A. Now in a similar manner, we can show that the image is also a linear mapping. Now next we will show that the kernel of A, if it is 0, if kernel of A is 0, then we need to show that A is 1, 1. A is 1. Now if kernel of A is 0, what does it mean? That whole set consists of only the element 0. So suppose ax1 is equal to ax2. To show that the mapping A is 1, 1, we need to show that if ax1 is equal to ax2, then x1 must be equal to x2. Now this implies ax1 minus x2 is equal to 0. As ax1 minus x2 is 0, we have x1 minus x2 is 0, and which implies x1 is equal to x2. So we have shown that whenever ax1 is equal to ax2, we get x1 is equal to x2. So when we have we have proved that if kernel of A is 0, then the map is 1 to 1. Next we move on to the definition of isomorphism. A mapping A from E1 to E2 is called an isomorphism if kernel of A is 0 and the image of A is E2. Or we can say that a mapping is said to be an isomorphism if that mapping is both 1, 1 and onto. Next, moving on to the definition of subspaces. A subset E1 of the linear space E is called a subspace of E if it is closed relative to the linear operations in E. That is, whatever operation we are defining in E, the same operations when applied to the elements in E1, we can form a subspace, we can form a linear space. So we denote it as E1 subspace of E, and clearly we can verify, or we can easily see that kernel of A is a subspace of E1 and image of A is a subspace of E2. Next, the definition of linear independence and dependence. First, we will define what a linearly independent set is. A set of vectors x1, x2, etc. xn is called linearly dependent if there exist numbers ai from I, where I varies from 1 to n, which are not all zeros, such that a1 x1 plus etc. plus an xn equal to 0. A set which is linearly independent will be a set which is not linearly dependent. Whenever a set is not linearly dependent, we call that set to be linearly independent. And this we have defined for finite number of vectors. Now we can extend the definition of linear independence to infinite number of vectors. That is, Infinitely many vectors x1, x2, etc. are linearly independent if for every k the vectors x1, x2, etc. xk are linearly independent. Now moving on to the definition of linear span. The linear span is the span is defined for a subset of a linear space. The linear span of a subset M of a linear space E is the intersection of all subspaces of E which contains the set M. Or you guys must have learned another definition also, that is the span of a subset is the finite linear combination of all vectors in it. I would like you guys to read theorem 1.1.2, and it is a simple theorem. We don't have to go for the proof of the theorem, and the theorem basically describes the dimension. Next we'll come to the definition of quotient spaces. So before defining quotient space, we have to define what a coset is. So let E1 be a subspace of E. We will consider the collection of subsets square bracket x is equal to x plus E1 where x belongs to E. Now all such sets, the sets square bracket x, such sets are called cosets of E. And for a particular subspace we can find many cosets, and the collection of all such cosets are denoted by E by E1. So we have a space of sets, or which are basically, instead of set we have a collection of cosets which is denoted by E by E1. Now when we give particular linear operations to this set, we form a space. That is, if we consider the operation, that is coset x plus coset y equal to coset x plus y, and a into coset x is equal to coset ax. If these two properties are satisfied for all the cosets, then we obtain a quotient space. And these are the things which we can verify very easily. That is, first thing is to show that two cosets will always coincide or they will be disjoint sets. Either they will coincide or they will definitely be disjoint sets. And the second thing is, two cosets x and y are equal if and only if x minus y belongs to E1. Try to verify these two things. Also go through example which is given in page number 6 of the textbook. I hope you have understood the things that are mentioned in these slides, and any clarification can be done in the next sections. So thank you, stay home and stay safe.